Swayam Prabha. Digital India. Educated India.
Welcome back, everybody. New topic today. We've seen how to put a chlorine or a bromine on an alkane. We've seen how to put a chlorine or a bromine on an allyl molecule. Let's see how we can put a bromine pretty much on a double bond. You might be thinking, we've done this before. Yes, we have, but we're going to do a completely different take on this. Okay, so here is bromination of alkanes, or hydrobromination, I should say. You also put a hydrogen, bromination of alkenes. All right, so what do we mean by that? Let's say this is my molecule here. We're going to put a bromine with HBr, and typically we put it like right here on top, but we're going to do a whole different twist on this. We are going to take this and put the hydrogen on the carbon that is fewer hydrogens, and bromine on the carbon here that's less substituted. You already know what type of reaction that is, right? Anti-Markovnikov. So for this you need a special reagent, which is a peroxide. If you don't have the peroxide, it's going to do Markovnikov. This is going to do anti-Markovnikov. Okay, so if you have HBr with peroxide, you're going to put the bromine on the less substituted carbon. So this is anti-Markovnikov addition. And let's see why that is. Why is it going on the opposite side just because you have peroxide? To see any kind of reason as to why you have a certain outcome in organic chemistry reaction, you have to study the detailed reaction mechanism. Then you come up with intermediates basically, and then that gives you kind of a window into the transition state, which will then give you the reasons for the change. So let's do the 3 quick and dirty mechanistic steps, which is initiation, propagation, and termination. All right, always this is going to be the same. So let's start with initiation. Join the gang. Initiation. In this case, you're going to take a peroxide, and you can use AIBN or benzoyl peroxide. Let's do benzoyl peroxide because that's what most of these textbooks have, although AIBN is also very, very popular in lab. So you take benzoyl peroxide, and then you split it apart. You take this and do the homolytic cleavage and go to their respective home atoms, and you will get a radical here. And this radical is quite stable because you can see it can do resonance with this carbonyl, which is very electronegative, and it makes it stable. Like your acetate, this is just like an acetate radical. In this case, it's benzoyl radical. So the benzoyl radical is now then ready to go attack your HBr. Your initiation is kind of 2-step here. You are taking this radical and you want to then make it into a radical bromine, create a radical bromine using that. So HBr is not just going to sit there in a bottle and say, hey, I'm going to become a radical. Something's got to hit it. And so the benzoyl peroxide here is going to hit it. Okay? And then you're going to get benzoic acid, which is just going to sink to the bottom. This is probably like CH2Cl2 solvent. So it's going to go into that CH2Cl2 solvent. That's your solvent. I'm going to write it down so you don't try to do all kinds of strange things with the solvent. So here your COOH, benzoic acid, it's going to go right to the bottom, and you will have a bromine radical. And this is the angry guy that's out to get 1 electron from anywhere in the world to get an octet. So here's your radical. Your radical then goes on a spree, killing spree, finding out other molecules that it can turn into a radical. Propagation, so it's going to find another molecule. Let's say a guy with a double bond here comes in, and that's the target. All right, so here is a bromine radical. It's going to look at this and it's going to add to this. It can add 2 ways. It can add to the top or you can add to the bottom. Let's add to the bottom here first and see what happens. If it adds to the bottom, I mean this carbon here, then this is going to go over here. And you might think, okay, here's a secondary radical. Why don't we take this hydrogen, put it over and make it a tertiary radical? And we just said, no. The angle's all wrong, so don't go there. No rearrangement in radicals. So you have a radical here, all right? Now this radical is then going to be a secondary radical. This bromine radical, this alkyl radical is then going to get even with HBr. Still mad at having made it a radical, and so now these guys just hold hands and form a bond right here. And so you form another bromine radical, which you know is going to do the same thing all over again. So you're going to get a bromine here and an H here, and you know this kind of looks wrong because you are expecting it to be on the most substituted carbon, but it isn't, mainly because your intermediate, when you attack here, is secondary and more stable. That's the whole reason for this. This bromine radical that's released is then going to go over and do the same thing. It's like a shuttle. Goes back and does this all over again, loop-de-loop, and so this is a chain, all right, reaction. Goes on and on until HBr runs out or your alkene runs out. So note, this is not part of the mechanism. If you add the bromine to this carbon, like so, then you are going to form a primary radical. And we just saw earlier that just like carbocations, your anion stability is going to be dependent on how many R groups there are to stabilize it and support it, because the radical is electron deficient. Therefore, this radical is very unhappy. It's like only one hand here to support it, whereas this radical's got two hands to support it. More friends, more hyperconjugation, more inductive effect, it's happier. Okay, so that's the reason for the selectivity. As I said, if you want to know the reason, you got to go through the mechanism. So this is going to be minor, very minor, I would say. It's mostly this is your major. All right, so that's just a note. This is not very happy. So now, once you've done your propagation, well, you run out of stuff, then it's termination. So you just go bang, bang, and kill all the residual bad radicals hanging around. So the cups are going to come after them, and bam, bromine and bromine come together, and they form bromine. Or you can call this, let's say, R radical and a bromine come together, which is what you want, and form a product. And depending on who's left behind, if mostly R's are left behind, the R radical and the R radical will just make an alkane. Okay, this is just a teeny part of it. The overall reaction is adding your propagation reactions together. So here, if you cancel out the things that are the same on both sides here, you are going to then get this plus HBr giving you this. That's your overall. So you see the same thing over and over again, because this is a chain reaction. It happens every single time in the same way. So HBr adds anti-Markovnikov, and the anti-Markovnikov is going to put the bromine on the less substituted carbon and hydrogen on the more substituted carbon, and that's your major product. Now, can we do this with HCl and HI? One of the steps on those reactions is an endothermic reaction, so they don't go as well. Whereas with bromine, both steps, this one and this one, are both exothermic. So therefore, this goes, like a shot. So whenever you want to do hydrohalogenation of alkenes, anti-Markovnikov, choose HBr, not HCl or HI. All right? Okay, so that's your overall reaction, and that's how you do that. Let's see what are the other reactions we can do that are very helpful. Since we talked about this peroxide radical, we can also do polymers with them. And this is a huge industry, as you know, all of your food storage, polystyrene, your carpets, your tires, your PVC pipes, your whatever you know, made of polymers. And it's just a simple reaction. You take this benzoyl peroxide, I'll call that RO, it could be any other peroxide as well. And you can, let's say you want to make a carpet. Let's say you take double bonded, this is propylene, and you have a initiation reaction again. This is going to put the radical on the secondary, and you start it off, RO. And you have a radical here. This radical is going to then react, so this is going to have a way excess of this and a teeny bit of this. So you have this huge industrial scale thing that's like, you know, maybe a few stories high, and there's a small hatch. You open the hatch and throw in some of this, and this will keep going on, and at the other end, you're going to be rolling out sheets and sheets of polypropylene, okay, or fibers that then they convert to carpets. This is then going to attack another propylene. And so this is going to go over here, and again every time it's going to then go make the most stable secondary radical. So you will have RO go over here and make a new one. So I'm going to put that new bond in a different color, and that's going to give you 1, 2, 3 carbons. Then you're going to have a radical. You're going to add to this another propylene, and goes on and on and on for millions and millions of these molecules. And this goes longer and longer, and you get a very long chain of polypropylene, which is basically carpet material being hooked together like this. And I'll put N. N can be billions, trillions. And you take these nice fibers, and that's what you see sticking out of your carpet, okay, these little things. And if you, let's say you don't want carpet, you want PVC pipe, same deal. You take this and polyvinyl chloride. Vinyl is just a double bond. And do the same thing, RO. Open the hatch, throw in some of this, and you have this millions of gallons of this, and goes on and on and on, and it'll go eventually and make these long PVC pipes. And that's connected to this with a chlorine. And because you have a chlorine, you're going to have this is very electronegative. It's very much harder. It's not as soft as alkyl groups. So here this is nice and pliable and soft, whereas chlorine is going to make it hard. And so that's why you get a pipe which is PVC. So this is how you get your PVC pipes. It goes on for billions and billions of these units as PVC. Well, if another very popular one is, since you're using so much of that for all your takeouts now with Grubhub and all of these guys bringing food to your door, well, what's that styrofoam thing? It's just pretty much the same thing, except here you're going to have a nice benzene, and you know benzene, you know, it kind of has a shape, and so this polymer is going to then have the same thing with benzene on it. So here's your double bond with a benzene, and so these benzenes can take space, and so then you have a nice squishy polymer. So here's your secondary, same thing here. And this goes on and on forever, okay? And so this is going to be your polystyrene, is what you call your food, the white coffee cups. This is styrene. So polystyrene is your coffee cup. And so you can keep going, and you can do styrene, polystyrene. You can do polyester, which are, you know, your clothes, paints, and so on. Okay, so there's a whole industry that's based on radical chemistry. Okay, now there's another huge application to radicals, which is probably something that you don't want, and so we're trying to phase it out. So these are what you have in your refrigerator coolants. You know, when you say fridge, the refrigeration comes from these molecules in those tubes, taking out heat from inside your fridge and then expanding, right? So, and then cooling and so on. So, when you are done with the fridge and you just throw it away, these are going to go into the atmosphere, and the CCl bonds can kind of split up like this and give you these radicals. So we are trying to phase this out, and we're trying to get alternatives to this, but it's kind of hard to do that. So here, let's say this one stepped out. Now this chlorine radical is the dangerous guy here. Okay, so you take this chlorine radical, when it's a molecule, it's fine. Okay, we got these in our system and so on. But when it's by itself, it becomes really dangerous. So it goes out there, and what does it do? It goes and hits a ozone molecule, O3, and the O3 molecule is the ozone layer that's really protecting us. And then that's going to hook up with one of these oxygens here and become ClO radical and oxygen. So you're pretty much converting the top nice beautiful ozone in the stratosphere into oxygen. Okay, so now the UV radiation is going to come through the hole and hit you and pretty much fry your DNA if you're on the beach without any suntan. So then your chlorine radical here is going to go after another ozone molecule, and this keeps going on and on. So you only need one chlorine radical here to go and attack like millions of chlorine radicals plus oxygen. Oxygen is good, but ozone is what you need to protect yourself. So this chlorine radical then is going to break up again and give you a chlorine radical and an oxygen, and this is going to do it all over again. So it's kind of a shuttle. It goes on in a loop until all of the ozones are destroyed. So you can see the ozone holes getting bigger and bigger, and more radiations coming in, and that might be the cause of the increased amount of cancers on the planet. So here, radicals destroy the ozone layer, which is why we're trying to keep away from solvents that have the potential of releasing chlorine radicals. The CF bonds are harder to break, so now we're trying to replace the CFCs with fluorines. A fluorine that is, for example, CF3, CHF, CF3. This is what now we are going to put in, because CF bonds are harder to break like this and create radicals. So therefore, we are going to use HFAs. So this is just a little blip on what polymers do to environment, the good and the bad. All right, so and it just depends on how we use it. I'll see you soon. Bye.